Should we start? Hey, hello everyone. My name is Kamyar. I'm Anima's student. She's not around today. She's traveling, so I'm going to take care of this session. I got cold like 2 days ago. If you do not hear me or you hear something like rumbling and it's not understandable, just let me know. And during this talk, I'm just going over some stuff related to generalization theory. And at any point, if you think that I'm talking about something which is not correct or obviously wrong, just let me know. Others are gonna help us to do it correctly. Okay. So the topic of this session is related to the really important question that we have in machine learning is as follows. It's like, I give you a set of data points and I ask you to do, like, let's say, classification or regression. And then you return some classifier, let's say. Let's talk about classification for now. And you return a classifier based on, or you train a classifier on your data set. And then the question is, this classifier you return, how close is this classifier to the best classifier that we could ever achieve? Okay? Or the performance of the classifier you came up with is close to the best classifier. If it is, how close it is. And if it's not, how we can realize that it's not. And it's based on this question, we can say whether did we do the classification task like correctly, and can we trust the classifier we came up with? Okay, so this is the main topic of this session. Is I have a data set, I do my classification task, and the question is, how good is the classifier I came up with? Okay. So before jumping to the generalization theory, I'm gonna just recap two things that Anima talked about in the other session. One is Markov Inequality. It's like, as we know, if we have like non-negative random variable x, which has mean expectation of x, we want to see how the tail of the x behaves. If we want to see what is the probability of that x is bigger than some quantity. And this is like Markov Inequality. If you massage this inequality, you can get many other inequalities that Anima showed about, like you can look at all the moments and you can get variety of different inequalities. One of the interesting inequality which comes out of this inequality is called Houghton inequality. Okay, Houghton inequality says if you have, I'm just putting a simplified version of it, it's like a bit more general than the one I wrote here. Let's say I have a random variable x, which is between 0 and 1. Okay, and I draw this. I draw from. It has some distribution, and I draw n sample out of that distribution, and I look at the expected mean or empirical mean, better word for that. And I ask this question that how. So if I look at the empirical mean, how far is this empirical mean from the true mean? Okay, and this one shows that actually the tail of this random variable, which is an empirical mean, is actually going down and vanishing exponentially in number of samples, as well as like how far I'm gonna be away from the mean. Okay, in other words, if I have some distribution, let's say this weird color is the distribution of the empirical mean. If I draw n samples, the chance that these samples are going to be far from the mean is going to go down exponentially. Okay? You can prove this one directly using Markov inequality. So Markov inequality is based off all these things. Any questions so far? It says that if I have a random variable, if it's bounded, I'm going to get, like, if I look at the empirical expectation, the deviation from the expected mean is going to be small. Okay, we use this inequality a lot. Okay? By the way, I'm gonna this slide's gonna be shared and on Piazza. Okay, so now this part is a recap, and let's formalize the problem that we are gonna study, which is, given a data set, I'm gonna train a model, and I'm gonna ask this question that how good is this model on like unseen data points. Okay? So the problem setup is as follows. We have a distribution P, which we are gonna draw our covariate X and the label Y, okay? And our goal is to find a classifier which, given a covariate X, tells us what is the label. Okay, so we wanna learn a mapping from X to Y. Let's say X is a image, and it's the image of a cat, and I'm gonna learn a classifier. When I apply that classifier on the image of the cat, I'm gonna get, let's say, like output label cat. Or if this is the image of the dog, I'm gonna get I'm gonna get label dog. Okay, so this is a problem setup. So we have a distribution P, which is on the space of like X and Y, covariates and labels, and these covariates and labels are drawn from this distribution. We are also given a set of hypotheses, or a class of like functions that they are gonna be, all these functions are gonna map. I guess I have this mapping. I don't. So they are gonna. Oh, I have it. They are gonna map the covariate to the label, and my task is, given this hypothesis class, I'm gonna choose, and given the data points, I'm gonna choose which hypothesis in this hypothesis class is going to be useful for me. Okay. Okay. By useful, I mean I need to define a loss function. I want to choose a hypothesis in this hypothesis class which actually, for me, minimizes some loss function. And the loss function is defined based on the prediction that my classifier has, or my hypothesis has, and the true label. Okay? So the output of h of x here is going to be a label, and I'm just seeing how far is this label from the true label. So this is my loss, and my goal is to minimize this loss, right? I mean, my goal is to minimize the expectation of this loss. So I have this loss on labels and my prediction, and I'm gonna come up with a classifier which actually minimizes this expected loss. Okay? That classifier is H star is the optimal classifier, which is our hope to find it, but we'll see that because we don't. The thing is, if we were able to compute this expectation over the loss function and get this capital L, which is like expected risk, then we could solve this optimization. By could, I mean assume that there is no computation bottleneck. If we could solve the optimization problem, we could find the best ever hypothesis in our hypothesis class. So nothing can do better than this one with respect to this loss. Okay? But in fact, what we have a bunch of samples. We don't have access to the true distribution. What we have, let's say, here n samples. I have data set of 100 cats, 200 dogs, 3,000 like airplanes, and 5,000 picture of like roads. Okay, so I do not have access to the distribution. What I have access to the data points drawn from this distribution. Okay, so but what I can minimize is, instead of expected risk, is I can minimize empirical risk. Okay, instead of looking at this risk, which I cannot compute because I don't have access to the expectation here, I can compute this guy, which is the empirical average of my expected risk, or we call it empirical risk. Okay? And then what I can do is like minimizing this guy. This is one framework. I can minimize this quantity, I can minimize the regularized version of it, I can minimize some surrogate loss I can do many things, but let's, for simplicity, for the simplest case, assume that we are interested in minimizing the empirical risk. Any part not clear because of my voice? Oh, good. Oh, good. Okay. So I'm defining, I defined these two quantities, I guess, right? Oh. Yeah, okay. So let's look at these two quantities. The first one is saying, if I find so h hat here is the like empirical risk minimizer, the one that we get from the samples, okay? And h star is the optimal classifier or like optimizer, and L hat is the empirical risk, and L is the expected risk, okay? So first question is somewhat saying, how far is the expected risk of the classifier I chose compared to its expected risk, okay? For each classifier, I can look at what is the empirical risk, and I can ask, if I had access to the whole distribution, I could ask what is the actual expected risk for that hypothesis. In fact, in practice, we cannot compute this one because we don't have access to the distribution, but what we can do is we can upper bound this quantity, okay? We can use similar things as I talked in topic related to the Hofstadter inequality. Hofstadter inequality says how far is my average compared to the expected mean. Okay, I have data points, like I have n data points, and I ask what is the empirical average compared to the true average. So this was the deal with Hofstadter inequality. Okay. But the thing is, here is a bit more complicated because this H is not something that I just choose without knowing what are my data. So if I know what is my data and do optimization on the top of that data and come up with this H, then I cannot use my Hofstadter inequality because the ID assumption doesn't hold anymore, or independence assumption doesn't hold anymore. Okay? The second quantity is called excess risk. What it says the best classifier I found in my data set, which is called H hat, if I apply this one on the real world, how far is going to be my expected risk compared to the fact that if I knew the H star and I was applying H star on the world. Okay? So what actually this one means is because I'm learning this H hat through the data that I have, which is not complex data. I mean, it's I don't have infinitely many data points. I'm gonna get H prime and H hat, and the question is, how bad is this H hat compared to the best hypothesis in my hypothesis class? Our main goal in generalization theory is to come up with the upper bound for this quantity, for the second quantity. Okay? If I can show that this is really low, and it means that if I apply the H star, which is the best I could do, and compare it with H hat, which is the thing I can learn it from my data points, how far these two are, and if the deviation is small, then I'm good, right? So I can claim that I found a good classifier. Okay? So in order to study this quantity, let's consider the simplest setting, which is not trivial. The simplest setting is everything is 0, so that we don't care about that. Something a bit still simple, but not trivial. Let's assume that the setting is realizable. It means that the expected loss of the optimal classifier is 0. In other words, my data points, they have structure that there exists a classifier in class of like hypothesis class that can like totally without any error separate the let's say these two classes like plus and circles. Okay? So this setting is called realizable setting, which means that we have a classifier which is like able to perfectly classify my data points, which in other words, it can be written in such a way that this actually gives me 0 loss. Okay? And for simplicity, also assume that the loss we are talking about is 0-1 loss. 0-1 loss means if my classifier predicts a label, and if the label is not equivalent to the true label, the loss is 1. If the label is equivalent to the predicted label, we say the loss is 0. Okay, so this is the definition of 0 loss. So here the loss is 0 because my classifier, which is this line, classifies everything to the left as a circle and everything to the right as a plus, and doesn't make any error, and it has 0 loss. So here I'm just showing you the empirical loss, but I couldn't find better picture in like on internet, so this is the best I could get. So yeah. And also let's imagine that the hypothesis class that we are dealing with is finite. It means it has, I don't know, 10 billion like hypotheses in it, okay? Or it has 10 billion like lines in it. We want to choose the best line like among all the lines in the hypothesis class. So we have 3 assumptions. One is realizable setting or realizability, which says data is separable somehow, and we are dealing with 0-1 loss, and also we are gonna deal with a finite hypothesis class. It means that the hypothesis class we are using has finite like members or finite elements. Okay? Any question about this 3 assumption? So this problem sounds simple, but let's see how good we can get in classification. Okay? And the questions I'm going to ask and then answer is, one is sample complexity. Is if I have n samples in my data set, and then come up with the best classifier on these samples, is this classifier going to give me like a loss which is like epsilon close to 0 or not? Remember that the optimal loss was 0, so we want to see how close we can get to the 0. So I want to ask the hypothesis I'm going to return, if I apply it on the true distribution, how far is going to be from 0? Okay? Or in another word, I can ask, after n samples, like with what probability I'm gonna be epsilon close to the 0 loss. Okay. So the algorithm we are gonna go through here is really simple. I have n samples, and I have a hypothesis class, and I ask. And in this hypothesis class, I'm gonna remove all the functions or all the hypotheses that they disagree with the data points in my dataset. Okay? So data point 1 has class 2. If there is a classifier in my class that assigns label 5 to the data point 1, I'm gonna remove that classifier from my hypothesis class. It means if I have a oops. Let's say this is my first data point. Thank you. This is my first data point. It has label 1. Okay? And I have a hypothesis class. Okay? And that's half of this hypothesis in this class, they are assigning label this, let's assume this is label 1. Let's assume that half of this hypothesis, when I apply them on x1, they are gonna give me label 0, and the rest gonna give me label 1. Okay, what I'm gonna do, I'm gonna remove all these guys, because I know that there exists a classifier in my data set, in my classification, like in hypothesis class, that is correct on all the data points. Okay, so if this hypothesis here, they are incorrect in at least one data point, I'm going to remove them because I can do better. I'm sure that I'm going to do better. Then I look at the second data point, and let's say this is 1. Sorry, let's say this is 0. So now I discard this part. I eliminate all the hypotheses here. I'm just looking at the guys here, and among them, for x2, these hypotheses here are gonna return 0, and these are gonna return 1. Okay, since they are like making wrong decision, I'm gonna remove them all. And then I look at the x3 and y3 and try to see there is a disagreement here or not. So through this, I just look at disagreements. If there is a disagreement, I just remove the hypotheses that they are like wrong in my labels. Okay. Why this is the case, why I can do that, because I know that there exists one classifier here which is correct on all the data points I have in the data set. Okay? So it means that after this elimination process, after n time steps, I'm gonna return a classifier which actually gives me a loss of 0, which is the empirical loss of that classifier is 0. Because if the classifier survives in this process, it means that that classifier didn't make any mistake on n data points. Okay, so now I'm going to return that one and say that's my return classifier or empirical risk minimizer, and that classifier is going to have like 0 loss. Okay, so I'm going to return a classifier which has 0 loss on training data points. Okay, but the question is, how good is that one if I was applying it on the real, like the whole distribution, the population, like the whole population of the data points? Any question? Good. Okay, let's see what we have next. So the probability I'm gonna study is this quantity, right? So it's a probability that if I apply my h hat on a real population or the true population, what is the probability that this guy is going to be epsilon wrong? Okay. To see how big is that quantity, there are like 2 or 3 simple steps, but kind of cool. One is, consider all the hypotheses in my hypothesis class that they are actually epsilon wrong. Okay? Then I can claim that the probability that the h hat gives me error bigger than epsilon is equal to probability that h hat belongs to this class B, right? So there exists a class B here, or it can be like this. This class B is subsection of my, or subclass of my like bigger hypothesis class. So B is inside H. Okay, but all the hypotheses in class B, they are like at most epsilon close to the true loss. I mean, like 0 loss. Okay, so all the hypotheses in this class B, they are gonna be at least epsilon, or at most, yeah, at least epsilon wrong. Yeah, it goes on. Okay. So now if I have hypothesis H prime or H hat, and then I want to ask like, what is the probability that the loss of this H hat is bigger than epsilon? this is equivalent to the probability that H prime is actually happen to be in class B. Okay? So we have this one, which is quite interesting and easy to see. And then I can ask, so now I know that these two quantities are like equal, so then I can ask the probability that the loss, so forget about this L here, like it should not be here. The probability that H hat is in class B is upper bounded by the probability that there exists a hypothesis in class B which actually gives me the loss 0 on training data sets. Okay? So I know that
I have a question.
I think there should be another assumption that
Yeah, because
yeah.
should the first one be H hat inside V rather than loss of H?
Could you say it again? Could you say it again?
Oh, that's fine.
Okay. So I made a strong statement here. I think it should be like all the subset of subclass of H, which L of, sorry, no, it's fine. Okay. So the probability that H hat, again, this should not be any L here. The probability that H hat is in B is actually upper bounded by the fact, by this probability, which there exists a classifier in B which gives me a loss 0. So if H hat is in B, there should be at least one which is 0. So I can write it as a somewhat union bound here. Okay. So now, if I know that, let's assume that a classifier H is in like class B. Okay, what is the chance? I draw one sample from my distribution, and what is the chance that that classifier is going to make a wrong classification, like wrong classification, like prediction? So I have a classifier H. Okay. I look at L of H. L of H is like expectation of like my Y and H of X are not equal, right? Okay. I can write this one as the probability that H of X is not equal to Y. Right? That makes sense? So, in other words, L of H somewhat gives me the probability of the mistake I'm going to make. If I'm going to deploy H, the probability that I'm going to make a wrong prediction is going to be L of H. Okay? So now if my classifier, which is going to make 0 mistake on n data points, it lives in B, the probability that my loss, so this one should be empirical loss, sorry, so that one is probability of the probability that my loss, my empirical loss, when I apply H on true data points is 0, it means that for n like samples, my function didn't make any mistake. Okay, what is the probability of that? The probability is like the probability of being correct times to the power of n, right? So I have a coin, I flip it, and the probability then is going to be like tail with probability L of h, this quantity, and it's going to be head with the 1 minus this probability, and I'm asking what is the chance of having n like head like n head like sequentially, okay? What is the chance? The chance is 1 minus L of h to the power of n, okay? And I know that L of h as assumption here is lower bounded by epsilon. I know that it's like the way I defined set B was the hypothesis they have like loss at least epsilon, okay? So I can upper bound this guy with this quantity, and you can write down and then write it as a e to the power of like minus n epsilon, okay? It means that the chance of if h, okay, if h hat had a loss bigger than epsilon, okay, the chance that I'm gonna make correct classification on n data points is going to exponentially go down, okay? This is good news. It's like if I'm gonna return a classifier, if the classifier is gonna be bad, the chance of being bad is exponentially low in number of samples. That's good news. Okay? But the thing is, this term I wrote here, okay, it's actually valid separately for each function in B, or each hypothesis in B. For each hypothesis in B, I can say the chance of making, each of them having like a loss bigger than epsilon is this quantity, okay? But I'm gonna return one of them, right? So, but I don't know which one. So I cannot say, so I'm gonna return something which is going to have this much, with this much low probability is gonna make mistakes, okay? What I can say, the thing I'm gonna return, I'm gonna say whatever it is going to satisfy this quantity. Okay? In other words, when I'm returning a classifier, I need to make sure, go ahead.
Maybe you forget to put a hat on the first F.
First F?
L, P, L, H.
Yeah, I said, I forgot to put that.
Oh, yeah.
Yeah.
Sorry.
Yeah, no problem, thank you for asking. Yeah, this is a typo. There should be a L hat here, and in order to make a statement, there is no need to have H hat here. So for any H in B, it's true, okay? Yeah, sure. But what I want this inequality to be true for all the functions in B, okay? Because I don't know which one I'm gonna return. So in order to make sure that the thing I'm gonna return has this property, I want to make sure that among all the possible functions in my function class that I'm going to return, this quantity, this inequality actually holds. What does it mean? It means I need to do a union bound. I need to return a bound which actually says the probability that there exists a function h in B that is going to be giving me like loss of 0 is actually upper bound with this quantity, okay? The sum, let me fix this, it's confusing. Not this one. Oh, sorry. This is correct. This one is H. And this one, as you said, is H. Okay. Yeah, thank you. Just let me know if anywhere is like something that makes no sense. Okay. We are out of typos, or we still have some? I guess we are good. Okay. So I'm gonna bound this probability now. which actually somewhat is saying that I want to see the chance of existence of a function in B which has 0 loss. I can upper bound this one with the fact that all the functions in B, they are going to give me 0 loss. Okay? And then this quantity is bounded by, for each of them, I know that it's bounded by e to the power of minus n epsilon. Since I have, in the function class B, I have B like number of functions, the fact that all of them are going to be true at once is going to be B e to the power of minus n epsilon. And this B is going to be upper bounded by H. H is the size of my hypothesis class. Okay? So I can say my classifier is in the classifier I'm going to return is going to be in class B, and the class B is the bad class, with probability that it's going down with e to the power of minus n epsilon. So it goes down exponentially. But it goes up with H. It means that if I have a gigantic class, okay, the chance that I'm going to find a classifier which is correct in more samples, but it might be incorrect in many other samples, is going to go high. Okay? So if I have, my classifier has like 10 classes, or my hypothesis class has like 10 hypotheses in it, after like seeing few samples, I can get rid of like 9 of them, and 1 of them is going to stay there and it's going to be optimal one. Okay? But if my hypothesis class has like, let's say 10 billion like hypotheses in it, after seeing 10 samples, I cannot get rid of like majority of the hypotheses in my hypothesis class. So I need more samples in order to make sure that I'm going to get rid of the wrong ones. Okay? So if I call this quantity epsilon, so delta, what I can claim is, after taking the log, I can say the probability that my class, the error of my classifier I'm going to return is bigger than epsilon is going to be logarithmic in the hypothesis class, the size of my hypothesis class divided by n. Okay? So if I gather like more samples, I know that with this super fast rate, I'm gonna get better and better classifiers. And if I make my like hypothesis class like from like 1,000 to 1 million, okay, but my bound is gonna get worse with log of this quantity, which is it's going to be 3 times worse. 2. Yeah, 2. So if I make my classifier like from 1,000 hypotheses to 1 million hypotheses, my bound is gonna be 2 times worse. So this is a quite interesting bound because of 3 main reasons. One is the dependency on the complexity of the function class I'm gonna use is logarithmic. It's like I can deal with gigantic function class. Since the dependency is logarithmic, I'm fine. And then the dependency on the number of samples is 1 over n. It's like if I double the number of samples, I'm gonna get 2 times better bound. The third one, which is super important, is like we don't have any notion of probability dependent on the right hand side here. I don't care what is the probability distribution here. The distribution that I'm training my classifier on doesn't appear on the right hand side. It means that any distribution you want to like choose, this bound holds. It's like whatever you choose, this is going to work. We call these types of bounds distribution free. So it's like you just go home and like look at my algorithm and go home and choose the worst case distribution that you can ever imagine, design for yourself, and apply this algorithm. Is not going to do worse than this. Any question? Okay. Okay. The thing is, this dependence on n, number of samples, which is like 1 over n, mainly appears here because of this realizability condition that we can eliminate things very, very fast. We can literally like very fast half the hypothesis class. But when the realizability condition doesn't hold anymore, which means that my best classifier also has some error, which is like loss of the H star is going to be non-zero, then I cannot eliminate, because even the best classifier makes some error. So I should not eliminate. So for that setting, we cannot get 1 over n. We get 1 over square root of n, which we are gonna look. Okay? So the thing we were interested, so now we are going beyond the realizable case and look at the thing we were interested at the very beginning. We were interested to see what is the expected risk of the classifier h hat I'm going to return. What is the deviation of the expected risk of the classifier h hat I'm going to return, and the expected risk of the optimal classifier. Okay? This was the quantity that we were interested in. In the realizable setting, this second term, L of H star is 0, so I was just bounding the first term, I mean the L of H hat, but now since it's not 0, we are going to keep it. There is a really complicated trick here, which is called adding and subtracting, which is like, what I'm going to do is I'm going to add this quantity and I'm going to subtract this quantity and add it, and subtract this quantity and add this quantity. Okay? So what I'm going to get is a cool thing, which is this one. So the way I came up with h hat, the way I came up with h hat was like through arg mean of L H H in H, right? Right? So if this classifier is going to be this classifier is going to be the classifier which minimizes my empirical risk, right? So L hat of H, if I look at L hat of H hat, this is the minimum loss I can get over all the hypotheses. Okay, so this one is bigger than for every H in, okay, including the optimal H. So even if I put H, H star, this is still true. So that's why I'm saying that this quantity here in the middle is like negative, okay? So therefore I can upper bound this left hand side with the first term in the right hand side and the third term in the right hand side, okay? That's the trick I'm using here. And again, if we go back and look at our Hofstadter inequality, what we are going to get is we have an empirical average of a random variable. Do you remember that x and y are random variables? Okay. If I apply a loss on x and y, this quantity is also a random variable. Okay. And since we assume that our loss is between 0 and 1. Okay, I can apply that the Hofstadter inequality at the beginning I wrote. Again, the Hofstadter inequality at the beginning I wrote, it was like simplified version. It's not the most general one. Doesn't need to be between 0 and 1 or IAD. Sorry, yeah. Okay, so here my random variable is this quantity, and I'm looking at what is the deviation of my random variable from its like expectation. Okay, through what's called Hofstadter inequality, we know that this deviation is going down exponentially in the number of samples. Okay, so I'm going to use this in this inequality to come up with the generalization bound. Okay, so here we said this quantity is upper bounded by the first term and the third term in the right hand side, right? So the probability that this quantity, which is the left hand side, bigger than epsilon, okay, the probability that this quantity is bigger than epsilon is upper bounded by the probability that the right hand side excluding the middle one is bigger than epsilon. Okay, because this quantity is bigger. Okay. So instead of studying this one, I can study this one. Maybe it's easier to study this one. Okay. This is kind of easier because if you look at this quantity, the first term, it looks like this. If you look at the second term, it's again looked like this. Here I put, instead of h, I put h hat. Here instead of h, I put h star. So that's main reason why we do it, because it's like simpler. Okay. Again, I don't know which one. If I know h star, I can claim I know the bound. If I know h hat without looking at my data points, I can claim that I know this quantity. Okay, but I don't know what is h star, and also I don't know what is h hat without looking at my data points. Okay, but what I can say for all the data points, for all the hypotheses in my hypothesis class, okay, for any if L of h, if I know the bound on L of h minus L of h for if I can come up with a bound that says for all the hypotheses in my hypothesis class, for all of them at the same time, the deviation of the empirical risk and the expected risk is bounded by epsilon over 2, then I can say this one is like for all the h's in h. Then I can say this is also true for h star, right? And also true for right? If I can show that for all the hypotheses in my hypothesis class, this deviation is less than epsilon half, then I can say also this inequality holds for the true, like not true, like the optimal hypothesis and the hypothesis I'm gonna return. Okay? Okay? So what I can say, I know that for each of them, this quantity, for each of them, if I choose it, this quantity is going to be like this, this quantity, I can write it here. I can say L of h minus L of h is bigger than epsilon half. With what probability? If I put epsilon here, I'm gonna get, this one holds with probability minus 2n epsilon square, right? Let's call this one, yeah, this is delta. Let's call it, okay? I'm gonna call this quantity delta over h. So now, if for each hypothesis in my hypothesis class, this one holds, then I wanna ask what is the probability that this inequality holds for all the hypotheses in my hypothesis class. So I can say with probability, I can do union bound again, and I can say for all the hypotheses in my hypothesis class, this inequality holds at the same time for all of them with probability sum over k equal to 1 to h, delta over h, which is delta, right? So with probability delta over h, it holds for one test. So I wanna, this inequality hold for all the tests, okay? So it means that I can upper bound the chance, the probability that all of them they hold at once by sum of the probability that they are not gonna be hold. 1 minus the sum of the probability that they are not gonna be hold. Okay? So there are some coefficients too as well. And then we can claim that even if it's not realizable and L of H star is not 0, then the deviation of L of the H hat, the one that I'm going to return, and the L of H star is going to be upper bounded by this quantity. The cool thing is, again, the dependency on number of hypotheses is like in the log factor. Bad side of this bound is, maybe we cannot do better than that, but it's like goes down by factor of a square root of n. Okay, so it's like store. So I need to have more samples in order to get the previous bound. But the good thing again is this bound is distribution free. So we don't care what's the distribution. Any question? So why we choose epsilon over 2 is, if this is bigger than epsilon over 2, this one is bigger than epsilon over 2, then the whole thing is going to be bigger than epsilon. So that's why, that's the reason to choose epsilon over 2. So far what we have done is like we say for each hypothesis class how fast we concentrate over its true mean, and then we do union bound to make sure that the concentration inequality we get holds for all the functions in function class at once, okay, and then we claim our bound. So it's like mainly 2 steps. First we come up with the concentration bound for each, given the fact that we know the hypothesis class, we come up with the concentration bound for that hypothesis class. So for that hypothesis in the hypothesis class, like how far is the empirical risk from the expected risk. And then we say, okay, this one holds for each function in the hypothesis class. I want to have this inequality for all these functions in the function class at once. Then I do union bound. I say, what's the probability that all of them they hold at once? Is going to be h times that each of them going to hold. Like h is the number of hypotheses in the hypothesis class. And then if these 2 deviations are each bigger than epsilon over 2, then the summation is bigger than epsilon, then I can claim that my excess risk is bigger than epsilon with the probability delta. Okay, and that epsilon is actually going down very fast. Okay, so I can get a really good classifier after seeing few samples. If my h is not big. I mean, it's not exponential in something. Okay? So far, what we have done here is 2 things. One is when we have realizable case, and second is when it's not realizable case. But for both of these settings, we just talked about the case that we are dealing with the finite hypothesis class. Finite hypothesis class are interesting for many applications in business and like marketing stuff, but in machine learning or many more like broader like settings, they are not that interesting because let's say my function is linear function. Okay, like we do linear regression or we do SVM. None of these are finite, right? The SVM we have a parameter w, which is going to be multiplied by my x, and I'm going to subtract and blah blah. So my hypothesis class is described by a vector w, which can be any vector in the ambient space of RD and is not finite, and the question is how we can like come up with the bound in the setting that the hypothesis class is actually not finite. So it's like super general. But before that, there is another setting which is super interesting to many people. Is the setting that even, let's go back to the finite hypothesis class, okay? But there are, let's say, 1,000 hypotheses there, but you know that the hypothesis number like 5 is most likely be the true hypothesis than hypothesis number like 25, okay? So you have some sort of prior knowledge. I call it prior here, P of H, which says for each hypothesis in my hypothesis class, okay, how probable is each of them based on my like domain knowledge, or some expert told me that like, hey, this hypothesis has been working for many years and it's like the best we have used. So I give some prior that hypothesis is going to be more probable to be the true hypothesis for me. Okay. For this case, similar to the past when we were using Markov inequality, we were substituting the delta for each. So we are using delta over H for each hypothesis, right? We were assuming that each hypothesis is equivalently probable. But if I replace this one with delta times P of H, okay, which I think you guys don't see. So instead of having this quantity be bounded by delta over H, I can say let's bound this quantity by delta P of H. Okay, if I bound this quantity with the P of H and then look at this summation, I mean do union bound based on this weight, which is kind of like weighted union bound, then I get K equal to 1 to H delta PH. Again, I'm gonna get delta. Okay, so but instead this time, instead of getting a bound which depends on log of H over delta, which is for the previous setting, we were getting here, we were getting log of H over delta, and when we were getting bigger H, we were like getting worse bound. Here we are, for each function in our function class, we are gonna get 1 over probability of that H times delta, okay? If the function is really more probable, is like we know that in our prior knowledge says that function is actually most likely is going to be the true one, and that probability is like 0.9, okay, then our bound is not going to scale with H. Okay, so if I have a prior knowledge and the prior knowledge is correct and is useful, instead of getting a bound which depends on instead of the bound getting such that it depends on log of H over delta, I'm gonna get a bound which depends on log of 1 over delta P of H, and if the H, I'm gonna return like P of H. If P of H is like 0.9, then the bound I get is almost independent of the hypothesis class. Okay, most of the cases it doesn't happen. We are not going to have prior knowledge of 0.9. We have prior knowledge of like something. I mean, it's way smaller than this quantity. We don't have a sharp prior on one like hypothesis. But if we had a really strong prior, we could do much better. Okay. This setting is called packed base. where we have some prior knowledge and we can get a better union bound. So all these things are in order to relax the union bound. So the most hurting part in all this analysis we have is the union bound. When you do union bound, you get a lot of like you get a hard and harsh dependency on the function, the size of your function class or hypothesis class. Okay. Any question on pack base?
If you go back to the slide, and then if you take like the uniform prior, which I assume would be like the piece you had before with the prior, but then you get like probably 1 over the size of H. So the bound would be the same, but then your probability would have an extra factor of the size of H.
If this one is uniform, PR of H is uniform, means I get 1 over H, right? So I get the same bound as you said, but what's the extra factor?
Like with probability at most. Previously it was at most delta, now it would be.
Oh, this is the probability at most. This one it holds for each H. Not for all of them. For all of them it holds for delta. Yeah, thanks. Yeah, with probability P of H times delta, it holds for each H, but when you do union bound with probability delta, it holds for all of them, but for each of them it depends on this quantity, and then what we are going to get our bound is going to instead of depend on H over delta is going to depend on 1 over delta PR of the H we found, H hat, and also H star. Okay? So how probable is H star and how probable is the one we found? Which gives us a better bound. Again, this one can hurt us a lot. Let's assume that the probability of the PR of the true H is close, like H star is close to 0. Then this bound is going to give us really, really bad bound. Okay? So now let's go beyond finite cases. Pack base also goes beyond the finite case. I'm not going to talk about it, but this like simple things. Not simple, I mean like in that setting. So if you remember, in the 2 slides ago, we looked at this quantity. Okay, and we said the probability that this quantity, which is like the excess risk, bigger than epsilon, is going to be equal to this quantity. Okay? So, and this quantity looks like the deviation from empirical risk for H hat, the empirical risk for the like H star. Okay? Which I don't know. But I can say, similar to the previous, like two slides ago that I did union bound, I can say that if I look at all the hypotheses in my hypothesis class and look at the worst one, the one which gives me the biggest error in the like empirical, like the deviation of the expected risk and the empirical risk, and look at the one which gives me the highest one. If I can bound that quantity, then I can bound for any other H. Okay? So it's like, if I can show that the upper bound, this one, the upper bound is, sorry, the supremum over all the H's, the deviation of the expected risk and empirical risk. If that one for the worst H is bounded, then I can say it's also bounded for H star and also bounded for H hat. Okay? So I have a hypothesis class. I look at the worst like hypothesis in my hypothesis class. See which one gives me the biggest error here. And if I have the biggest error for that one, then I can say, okay, I have the biggest error for the H hat and also H star. Okay? Make sense? So now I need to like come up with the upper bound. I mean, I need to analyze this one, okay? The interesting thing is, we can show that if I call this function as function g, the g of h and l and n, number of samples, is actually this supremum over h in h and L of h minus L of h. Okay, if I call this quantity g, people have shown that the expectation of this quantity is 2 times of Rademacher complexity. And what is a Rademacher complexity? Rademacher complexity is this interesting quantity which says in the whole function class or hypothesis class, okay, look at the loss you get out of samples xi's and yi's, okay, and multiply them by a random variable called sigma I, and this random variable is called Rademacher random variable. It's with probability half is 1, with probability half is -1. It's like switching, okay? And you look at the maximum of this quantity over all the hypotheses in the hypothesis class. And just make sure that, I mean, the interesting part is the expectation is outside. So for any set of x and y's and sigmas, you want to find the best hypothesis, okay? Which by best, I mean which maximizes this quantity, okay? I'll give you a few seconds to see. This quantity has quite few interpretations. One says let's assume that your labels are -1 and y, and -1 and 1 based on the sigma, okay? And you multiply your loss by 1 if the label is 1, and loss by -1 if the label is -1. And you somehow want to fit to this randomly generated data labels. In other words, what I mean is let's say this is my distribution of x's in a natural setting. These are all pluses and these are all circles. Okay, mainly the setting is like that. But what if instead of getting this this pretty separable or nice distribution of labels, you would have gotten something weirder, which is so for this one is literally let's imagine the constellation stays same. I'm drawing same data distribution of covariates. And now the labels are literally randomly generated, right? The labels are randomly assigned, okay? And Rademacher complexity somewhat is capturing the fact that if I assign my labels randomly with Rademacher random variable plus and minus, what is the best classifier I can get from here? Okay, if the class of the hypothesis class I'm dealing with is super small, it's has really restricted function class, and it can either give me this one or this one or this one, okay? So the best hypothesis in my hypothesis class cannot do much or cannot minimize the loss a lot here. Okay, so is my best classifier in my hypothesis class is not gonna do a great job on this random noise. But imagine if I had a really, really rich classifier which could classify which could come up with this classifier. So then this classifier is going to give me like bigger, like higher value of Rademacher complexity. Okay? So Rademacher complexity somewhat is capturing the fact that how well I can even like classify a random noise or random labels. If I'm able to classify a random label, then whatever label you give me, I cannot trust my classifier because it's like almost always overfitting. Okay, so that's somewhat what is capturing. It's not exactly this one, but it's like some interpretation. So my Rademacher complexity is going to be super high if my function class is super rich that can even overfit to the randomly generated labels. Okay, if I just randomly generate labels and I can perfectly classify the random labels, then my function class is, for my function class is super easy to overfit. Okay, if I overfit, I cannot say I'm generalizing. Okay, if I give a zero loss on my like training data set and my Rademacher complexity is super big, then I cannot say, hey, I'm generalizing, because I could even fit a random noise, and if I fit a random noise and give you zero loss on the random noise, then I cannot say I can do better in like real like data points or real like another generation of random noise. Okay, so if I give you this classifier which gives me zero loss on random labels, if I draw another random label, this is going to give me like almost worse like classification error. Okay, so this one shows how well I can fit the random noise. Okay, and I don't want to deal with a function class which is like that rich. Any question? And also look at this, the fact that here, let's say I have like 100 data points, and I have a function class can like fit here. Okay, but if I increase the number of samples, more samples, okay, then maybe my function class is not rich enough to overfit to these data points, so I'm gonna get better Rademacher complexity. So what is my hope is my Rademacher complexity is going to go up as I make my function class richer and richer, and it's going to go down as I increase the number of samples. Okay, so I'm expecting that my Rademacher complexity be like a function of number of samples and like some property of my function class and like loss. And I know that intuitively that this one is decreasing, or is a decreasing function of number of samples and increasing function of like complexity of my function class. Okay, then we can show that for a general class of functions, my excess risk is going to be upper bounded by 2 times Rademacher complexity plus this quantity. Okay, this quantity is also going down with the factor of 1 over square root of n. And this quantity comes out because the Rademacher complexity is expectation of this quantity g I wrote, but what we care is like tail bound over g. Okay, so Rademacher complexity is expectation of this guy times divided by 2, but what actually we care is how far this one is away from this is true mean. So this part is just something coming from McDiarmid like lemma, but you can imagine it's like a Houghton inequality. It is not, but something similar. Any question? Okay, so so we covered like finite hypothesis class, and I didn't prove this theorem. It's simple. I mean, everything I talked is coming from this note by Percy, and it's really intuitive to like intuitively written, and it's like cool to read, and whenever I read it, I enjoy it. I didn't prove this theorem for like general hypothesis class, but almost the remaining part of the whole generalization theory is for this general hypothesis class, and people have done many works to see what is this random error complexity for different problems. Let's assume that my problem is binary classification. Is either like cat or dog, okay? For that setting, people have shown that actually random error complexity is upper bounded by something which has this form, which depends on the VC dimension of your function class, okay? And divided by n, like a square root of it, this one. So it's like, and VC dimension is, if I give you like data points of from my distribution, like for what situation, for how many situations of like labeling of plus and minus like labels, for how many constellation you can like perfectly classify. If the number of constellation that you can perfectly classify given a like function class is big, means that your VC dimension is big. It means that your class is really powerful and rich. Okay, we like our class be somewhat rich, but not too much. Okay, so VC dimension for binary classification means how many constellation your class can like perfectly like classify. Okay, if I have 2 points, okay, and mainly if I have linear functions, linear function class, this VC dimension is linear in dimension. Okay, if my linear function, I'm working on the linear classifier, binary classifiers, and the dimension is like 1000, the VC dimension of that function class is 1000. Even though the function class is continuous, it's big, but, and like, it's not finite, but what I'm gonna get is going to be something small, okay? But mainly in like many classification problems, the dimensionality of the input is like few million or few billion. So then you cannot like hope that it's going to be a good measure, okay? So for binary classification, random error complexity is upper bounded by this quantity, which is interesting. For linear classes, I said it's going to be d log 2d over n, I think, if I'm not wrong with a factor 2. And let's say this is my linear class, but I say the L2 norm of my linear class, which is W I wrote up there, let's say is W, with some norm is, let's say P norm, is bounded by some quantity beta. Okay? Did I use beta here? Yeah. Beta over C. Okay? And let's P is 2. And L2 norm of your x's and y's is also bounded by C. Okay? Then you can show that actually your random error complexity is bounded by this. If I make sure, or let's say I do linear classification and I put a like L2 regularization. L2 regularization somewhat is constraining my function class, okay? And even if I live in like billion dimensions, but if I make sure that the norm of my W is bounded and the norm of my covariates and the labels are like bounded, okay? Then what I can get much better like random error complexity. Okay, I can squeeze down really fast, almost exponentially my function class. Okay, so the works in generalization theory are like many this type that you come up with the random error complexity for many different function classes or many different problems, or you try to come up with some bounds even better than like random error complexity. Like random error complexity came out like I think 20 years ago. But you can cook up better bounds based on different problems. Okay? Any question? Okay, I think, yeah, I think yes, we call it. Thank you.